Okay, thank you everyone again for joining one more week to this seminar. Today we have Miguel De Carvalho from University of Edinburgh, so I hope you enjoy the talk. What's yours?
Okay, thank you so much, Nico, for the introduction. So welcome everyone who is here today, and welcome also who is on to our participants online. And so before getting started, I'd like to go back to the title of today's talk, and I'd like to start with a few keywords that are on the title of today's talk. So as you can anticipate from this keyword in here, so there will be ideas related with extreme values. And so that's a part of the talk. There's definitely ideas in here related with not just univariate extremes, but also some ambition also to model how extreme values relate together and what's their multivariate distribution. And on top of that, there will be in here some time-changing aspects that I'll be exploring over today's talk as well. So, and in order to model the time-changing nature of multivariate extremes, I'll be also introducing some ideas, concepts, and methods from Bayesian smoothing as we move along, because essentially what I will be developing here over today's talk will be a Bayesian smoothing approach for modeling time-changing bivariate extremes. I'll be mainly focusing on the bivariate extreme scenario. I also have some comments that I'll be making in passing related with how we can also do this in terms of multivariate extremes as well. And there's also I would like also to acknowledge also this is joint work with Junoli and Antonio Rulli. Junoli, my former PhD student, now working at a financial regulator. Antonio Rulli is from the European Central Bank, and also Julio Avila, who is in Chile. Okay, so let me get started, and I want to start first with also the motivation and what are the goals in terms of works related with extremes. And extreme values and extreme events have been on the headlines again and again, and unfortunately, but we all been seeing these events on the headlines for the worst reasons. So including wildfires, also including earthquakes, and also including other extreme events, and even extreme events of a financial nature. From the point of view of today's talk, I'll be mainly concentrating in terms of applications, in terms of finance, but the methodologies that I'll be discussing here today do apply more generally to other applications as well. And what I would like also to introduce you is also to the topics in terms of where this community has been growing, and in terms of books and references that are available. So this is a community that has been producing quite a bit of also monographs on the topic. There's also quite a bit of developments in terms of survey papers as well as in terms of other points that I would like to mention, including also software as well. So this is just a list where you can find resources related with models for multivariate extremes fitted in R. So this list is not exhaustive. There's many other packages that are available as well. And this is just a review paper where you can find more about some of the software that has been developed for extreme value analysis. And we also have, as many of you know, of course, we also have just a journal just dedicated to the field as well, and that is Extremes. That's the name of the journal. These are the key events in terms of community EVA meetings, which have a long tradition. So would like to just mention that this is the scope in terms of community, in terms of the work that I'll be presenting here today. And you might be asking also, what's the big deal about extremes? What is really extreme value theory looking for? And I would like to start with the most obvious example on what we know already, that when we have a random sample and we know that the empirical distribution function is the worst example we can actually have in terms of extrapolating beyond the observed sample maximum. Whenever you fit an empirical distribution function, you know that the probability of exceeding the maximum is actually zero. In other words, this probability in here will be equal to zero for any positive epsilon. In words, this of course means what we know already, that the empirical distribution function has no ability to see beyond the observed data, and hence it has no ability to do extrapolate into the tail of a distribution. Extreme value theory, on the other hand, is really motivated by this problem. How do we go about extrapolating into the tail of the distribution beyond observed data? And we might do this on a univariate framework, but we might also do this in a multivariate framework, as well as in a spatial context. And this is the key goal in terms of multivariate, in terms of extreme value theory. How does the field, what are the tools and techniques that allow us to do that? Well, the most elementary result on the field is a so-called Fisher-Tippett theorem, which essentially shows that actually the sample maximum will converge in distribution to a generalized extreme value distribution with parameters mu, sigma, and psi, where mu is a location parameter, sigma is a scale parameter, and psi is a shape parameter known as extreme value index. And this parameter is essentially the parameter that is controlling the rate of decay of the tail. Essentially, the case psi greater than zero essentially corresponds to the situation where you have heavy tails. Case psi equal to zero would be the case where you actually have, for example, maximum of sample maximum. When you take sample maximum of normal distributions and you suitably standardize that sample maximum, then you actually converge to this case where you have psi equal to zero, whereas psi being negative essentially would correspond to situations such as when you consider sample maximum of, for example, beta distribution. So these are the so-called Freche, Gumbel, and Weibull domain of attractions. Okay, and this would be, of course, the starting point for the extrapolation when you have the univariate framework. And there are similar ideas that then you can use for also building extrapolation principles, seeing beyond the observed data, extrapolating according to extreme value theory. Paradigm based on multivariate extremes. However, you will no longer have something such as the generalized extreme value distribution, which is a 3-parameter family. So when you need to model multivariate extremes, you would have actually your object then describing the dependence becomes a complicated object. It's no longer like in the Gaussian world. In the Gaussian world, you have the variance covariance matrix. In order to describe the dependence between the extreme values, you would need actually a parameter known as angular measure, which is itself a probability measure on the unit simplex. Okay, so this is essentially the warm-up, the starter, if you will, and I'll come back to it as we move along. And I would like just to highlight here perhaps also something which is also relevant, I think. At least I get this question quite a bit of times in practice. Many times I'm asked, oh, but extremes are just rare events. So, well, yes and no, you have to be careful. This is just simulated data from two-component mixture model. minus 10, and 10 are actually just shown in here. So these are just the two components, and the mean of this component is minus 10. The mean of that component is 10. All values in here surrounding 0. In a small neighborhood of 0, they are rare, but they are not extreme. So in other words, everything that I've been mentioning in here in terms of extrapolating, I'm really thinking in terms of extrapolating in terms of either the right tail, the left tail, the joint tail, but not really in terms of these sort of situations. That's a different thing. What we're seeing in there is something which is rare. However, it is not extreme. It is not a tail event, whereas the methodologies and ideas that I'm discussing in here today, they are definitely associated with small probability events, but with tail events and not just with any type of rare event. Okay, so that's a disclaimer I'd like to add as well. And what I want to do today is to present here a Bayesian time-varying model that learns about how the dynamics governing extreme values evolves over time. Okay, so this is the purpose of this talk, and my starting point for this will be the following. I'll start with time-varying versions of some mainstream measures of tail dependence, and particularly I will start by introducing these, assuming that X and Y have common marginal distributions, and assuming that they have common endpoint in infinity. In other words, essentially, you can think about many times, it is common to actually think about these X and Y as being, for example, just unit Frechet. So I mentioned already that this is the Frechet domain of attraction. Unit Frechet is a canonical GV distribution, so it's just GV111. Okay, so whenever I refer back to unit Frechet, essentially I'm just referring to this distribution, this canonical GV distribution. And it's similar to coupled world. In coupled world, you standardize everything to uniform margins, standard uniform margins. In extreme value theory, it's common to standardize everything into a GV unit Frechet scale, which is same thing as saying GV111. Okay, so just wanted to mention that if I mention again unit Frechet, you will know that this is unit Frechet. Okay. So the standard measures that are available in the literature, these chi and chi bar are defined as follows. So what is chi then? Okay, chi is just the probability of X to be extreme given that Y is extreme. Okay, so that's really just the definition. So we're having a look at the conditional probability of X to assume a large value given that Y assumes a large value. I'm taking here the limit as U goes to infinity because I'm assuming that the upper endpoint is infinity, and you start seeing the need for converting everything to the same scale. Otherwise, being extreme on one margin would not imply being extreme on the other margin. So you start seeing where this assumption is hidden. So also there's another measure of extremal dependence, which is given by chi bar, and which is looking like this. So why do we need two measures of dependence between extremes, you might ask? Well, in order to explain that, I think it helps really to go back actually just to chi itself and to understand that there's a subtle point in here. When chi is equal to 0, that is when this limit is 0, the variables are said to be asymptotically independent, okay? Whereas if chi is between 0 and 1, then the variables are said to be asymptotically dependent. What does this mean? Well, we're actually having a look at the dependence between, so when we condition here over this region for a very large U, okay? And we're essentially just getting this region to go to infinity. And asymptotic independence essentially means that the dependence fades away as the threshold goes to infinity. So as you keep increasing more and more the threshold, if the dependence fades away, if it goes to zero, then we say that the variables are asymptotically independent. If there's still dependence in the limit, then we say that they are asymptotically dependent, okay? So for example, when you take a bivariate Gaussian coupler, essentially you are in this situation. No matter what value of correlation you take, even if you take correlation equal to 0.99, unless your correlation was really exactly 1, you will be in the situation of asymptotic independence. That is, you simulate data from your Gaussian couple, even with correlation equal to 0.99, and the dependence will fade away in the limit. Okay? So, in other words, asymptotic independence might seem like something which is unnatural, but no, even with Gaussian couple, you might have that. When you have an extreme value coupler, however, actually you are typically in this situation of asymptotic dependence. Okay, so now if we go back to this idea that okay, so Gaussian couple is an example on where you can have asymptotic dependence. So the question then becomes, how do we measure dependence inside of the class of asymptotically independent random variables? Okay. This is where the second measure enters, okay? So the second measure is assessing the dependence between the extremes under the class of asymptotically independent random variables, okay? And what it can be shown is that actually this chi bar will be equal to correlation when you have a Gaussian bivariate couple. In other words, chi bar is itself equal to correlation when you actually have the Gaussian couple, and chi bar is assessing whether you have positive or negative dependence between the extremes whenever you have asymptotically independent variables. Okay, so we have to deal with these two worlds, asymptotic independence and asymptotic dependence, and we have to work with those. So my starting point in terms of motivation in here, applied motivation for this work, is a pair of seminal papers written by Kuhn, Rockinger, and Ton, both published at very good journals. So this is one of the top journals in finance. So in finance, you have Journal of Finance, Review of Financial Studies. This is Review of Financial Studies. There's many other good journals in finance, of course, but this is one of the top journals in finance. This is another journal that they published a few years ago at Statistica Sinica, and essentially where they apply these measures of that I've just introduced before to stock markets, and they make some interesting findings after applying these measures. The catch, though, is that we all know that things are not static, things evolve over time. So the question is, what happens, for example, under a period of stress? When you actually have extreme losses increasing, do you actually have higher dependence between those extreme losses or not? How do things change over time? How does dependence between the extreme losses in stock markets get affected by other exogenous reasons? So things might be changing. Whereas if we just have a look here at chi and chi bar, we just get a static overview of what would be happening in terms of dependence between extremes. And of course, think that also in terms of from an applied point of view, this is key. Because if you think about X and Y representing, say, two stock markets or two assets on your portfolio, well, one thing is having one extreme loss on one. If you're actually investing on both, and if you have a joint loss on both, that means risk. Okay, so that means that you're having a loss not just on one stock, but you're having a loss on more than one stock on your portfolio. So this region definitely is very important from a financial point of view as well. Okay, then what is the scope on in terms of this literature? This literature contributes to, this paper contributes to this recent literature on multivariate non-stationary extremes, whose focus has been in terms of learning dynamics of extremal dependence over time. So this is an object that we've developed and that has been also explored in the literature by others as well. We call it the spectral surface. And remember when I was mentioning earlier that when you model multivariate extremes, that there's a probability measure describing the dependence between the extremes. This is then a time-varying version of that probability measure. And the more mass you have closer to this value 1/2, the higher the dependence between the extremes. So if you think about this X representing time, what you would be seeing according to the surface would actually be an increase in the dependence between the extremes over time. I will be mainly focusing in terms of interpretations in terms of time, but other covariates could also be of interest. But keeping in mind also the applied scope of this work, and because I really would want to go back to Punrockinger and Ton, I will be mainly focusing in terms of time as being my natural covariate in here. Okay. So what are we bringing here to the table? So I would argue that, okay, so definitely we don't need to assume what other have assumed in terms of working in the class of multivariate extreme value distributions. And so that is really good because it then allows us to deal with both asymptotic dependence as well as asymptotic independence. I think that's an important point. I think this is also something key because this is really as easy to fit as a generalized linear model, as I'll show next. So, and I will also not be showing here simulations today, but we have evidence suggesting that this would be at least in terms of at least as reasonable as fits that could be produced via this approach, and definitely dominating in quite a few situations. I would argue that this is also an important point because we define priors on the space of parameters of interest, that is in terms of time-varying versions of chi and chi bar, whereas if we used this sort of approach, we would have to define priors on a complicated space of functions, where we would need to introduce a set of constraints that are not so easy to introduce. Okay, so this is background. I've told you what I am to do. Now I'd like to give you the details on how I'm actually implementing and what is the concrete embodiment of this idea. So there's a discrete time bivariate stochastic process that we will be in here, assuming that is in unit Frechet marginal distributions. If it's not, we convert it to that scale, just using standard tricks. And let's define here the time-varying coefficient of extremal dependence function. Of course, the definition is just straightforward. There's nothing in here really challenging in terms of making the definition. Definition is really straightforward extension of the previous measures that I've introduced earlier. So I'm just making this clear that these are the measures that we'll be considering next. So these are the extensions of the measures that we will be seeing in here. I want to also highlight that in a few of these charts, I'll be rescaling time to the unit interval just for the sake of convenience. So, but that's essentially just for convenience reasons. Okay, so if you see not time ranging from 1 to n, but rather from 0 to 1, that's just for a matter of convenience. Okay, so there's nothing really challenging in terms of defining really these measures. This is just one example, just a working example. So this is just an example associated to a bivariate extreme value distribution known as logistic family. Okay, this is then the same thing as just as in a Gumbel coupler. And what we're doing in here is then just thinking, okay, so if we actually have then the parameter in here, this parameter which is controlling and governing the dependence between the extremes, well, if this looks like this, then the corresponding chi-t would look just like this. So we would always be under the regime of asymptotic dependence, and chi bar itself would just be static here at 1 over this example. Okay, this is just one warm-up example, just illustrating the previous concepts as well. So how do we go about modeling this? So okay, so chi t and chi bar t now are functions. So if we need to model these functions, and in these functions, then we need to define priors on these function spaces, on which chi and chi bar t live. And essentially, the construction will be based on the following idea. So there's a semi-parametric flavoring into it, but just in the sense that there's an inverse link function that we'll be considering, as well as then a smooth function that we'll be considering in here. Okay, so the idea then is as follows. So the idea is really just to go back actually to the definition of this probability. This is a probability. This lives in 0, 1. So I'm essentially just doing this specification in order to model this probability itself. What is really the idea? The idea is really to use this inverse link function, so to enforce actually the constraint that this needs to be between 0 and 1. Okay, so this inverse link function will enforce that parametric constraint that chi bar t needs to be between 0 and 1. Okay, whereas the smooth function itself will reflect the effects of time on tail dependence. So essentially, this is just then governing how the transition evolves over time, how the dynamics of extremal dependence is evolving over time, whereas f itself is just enforcing that everything is really between 0 and 1. Okay, so that's essentially the approach that we take in terms of modeling then that probability itself. In terms of chi bar, we play the same game again, similar formulation. We go to chi bar and we just say, why don't we do the same thing? We know that now chi bar needs to be between -1 and 1. Okay, remember that between 0 and 1, it will mean positive dependence between the extremes, and between -1 and 0, it will mean negative dependence between the extremes. And we take advantage then of well-known results in terms of that go back to formulations that were studied by Ledford and Jonathan Thorne, that allow us to think about the following, allow us to think that it would be convenient in order to again enforce the constraint in a similar way. It would be convenient to write this in this way. Remember that why? Remember that chi bar itself is written by definition as 2 times the limit, which we approximate in this way, -1. This is where the formulation then comes from, essentially because the rationale underlying it is that actually to think about that ratio that appears in the limit, and this is a well-known quantity that has been studied, and it is known as coefficient of tail dependence. And this is then typically modeled using the following formulation. Well, a static formulation, which is here extended, and which is just considering then the probability of the mass in this region, in the joint tail, as being described by the probability of a univariate z. This zt is simply given by the minimum between xt and yt, and essentially then it's just modeling that as if it was a Pareto type model. Okay, so what we're saying is that the mass that is left in here, as you increase u, and when you consider actually that the zt is equal to the minimum between x and y, then you can convert everything into a univariate type of problem, and essentially you are just assuming that this decays as a Pareto would decay, and there's a bit more of flexibility with respect to just Pareto, because we're adding also in here this time-changing slowly varying function as is common in extremes. Okay, but the long story made short, the same idea comes again, because this link will enforce now the parametric constraint that this chi needs to be between 0 and 1, whereas then the smooth function will govern the dynamics, the evolution of the dynamics over time, and will control how it evolves. Okay. Now, if we're Bayesian, we have to think about what is the likelihood associated to this model, and the likelihood can be written like this. So we can actually see that actually for conditional on u being large, essentially what we have is the following processes of interest. I'll call them yt and et. Essentially, yt is just being indicator function on whether xt is an exceedance or not, conditional on yt being greater than u. In terms of et, it can be easily shown that actually is logarithm of zt, remember again, is minimum between xt and yt. Well, conditional on zt being greater than u can be easily shown that this is actually exponential distributed, again, for large u. So this is approximately exponential distributed for large u. So this is then used as the approximate likelihood on which then the inference is based. And the inference goal is to learn about chi-t, not from all data, right? Because it's just from data from the extremes themselves, which are essentially then just the pseudo samples associated to these processes that I've defined just there. Okay. So, how do we go about learning about these parameters of interest? So we already have likelihood, and okay, how do we really model then the g function and the L function that are controlling and governing the dynamics? What I'll be doing here will be the following. I'll be just using B-spline basis functions. So I have T0 to Tm internal knots, equally spaced in my case. And what I'm depicting in here are all the basis functions, okay? The B-spline basis functions being depicted here, cubic B-splines. And then there's the coefficients associated to each of these basis functions in here. So the coefficients will be multiplied by these basis functions, and we'll be getting these basis functions to go up or down, and they will be allowing me to control the dynamics of extremal dependence over time. Okay. So in other words, these coefficients, which will be then the coefficients, the parameters that we'll want to learn from the data, are just then governing in here the way that these functions go up or down, and this is then the way to then model the dependence over time. Okay. Okay, so this is then, we need then a prior in terms of these parameter beta, the parameter beta that I've just shown there. And what we'll do is we'll use Bayesian P-spline approach of Lang and Bresger. So what we'll do is, in terms of the neighboring betas for the basis functions that I've just shown before, the neighboring betas will just use the first order random walk prior. Essentially, what this means is what I've just wrote there, and the random walk prior, then depending on this parameter in here, this parameter is essentially governing the smoothness of the curves that are fitted. Why is that? Because if actually this parameter is set very large, this variance is set very large, then you actually get that the neighboring betas, the ones corresponding to the basis functions, the neighboring basis functions, they could vary a lot. Whereas if you get very small variance, then that means that neighboring coefficients, they will look very, very similar. Okay, so that's standard in terms of P-spline formulation. Then we're having a flat prior in terms of the initial coefficients. And so, as I've anticipated already, this parameter controls degree of smoothness. And so what we do then is that we will set an inverse gamma prior with hyperparameters A0 and B0, and just using then standard specifications in terms of those as well. Okay, I'll be quick in terms of highlights in terms of sampling from the posterior, but this is very, very straightforward. The key points are in here. So in terms of tau, the parameter controlling smoothness, this is conjugate inverse gamma posterior. In terms of sampling, this will be just equivalent just to fitting two pairs, two measures that correspond to two generalized linear models. So the metropolizing algorithm, it will be based on iterative weighted least square proposals, as it is standard in terms of generalized linear models. And that's an old trick by Danny Gammerman. And actually, I just wanted to highlight that in terms of chi-t, when the link function is just of this type, then we can actually use this standard latent trick specification, in which case we really get the gift sampler, because this is conjugate, and we would get also conjugate for beta itself. Okay, so data, and let me show this in practice. So the motivation, coming back to the motivation that we've had in terms of finance application. So we'll analyze 6 stock markets across Europe, East Asia, and North Africa. And data are gathered from data stream and cover this sample period. So that means that it covers periods of stress, such as, for example, the already COVID-19 crash. Of course, other well-known periods such as subprime crisis, but also dot-com bubble, and so on. So it's already long enough to contain some interesting events from a financial perspective, and we'll be focusing in here in terms of negative log returns, as these can be regarded as a proxy for losses. I think I would have just time to mention that. So essentially what we mean is that whenever you have this would be just log returns, and what we're taking is actually negative log returns. And the reason being, well, this is no overlapping. Third then? No? Okay.
You could use some scrap paper and the document catalog, but then the online people could see it as well.
Okay, I think I'll skip that. I'll just say this in words then. That's okay. So let's improvise. We all know, good old Taylor theorem, we all know that logarithm of x is approximately x minus 1. And so from there, we actually see that logarithm of pt divided by pt minus 1 is essentially just the same thing as pt divided by pt minus 1 minus 1. So what I'm trying to say is that using Taylor's approximation, we can actually see that this is approximately just, and this will be my final attempt to pt. This is approximately pt minus 1 divided by pt minus 1. Okay, so this can be, in other words, so daily returns are just approximations to daily log returns are just approximations then to returns themselves when this ratio is close to 1. So just using Taylor approximation for x close to 1. Okay, so when you take this, I know that this is difficult to see, but I hope that with the explanation in words that was clear. When you actually take not returns, but when you take minus RT, and that's a proxy for losses. Okay, and that will be our unit of analysis in terms of this application. Okay, so moving on. So I will be adding also a few reference timelines here in the analysis, particularly beginning of stage 3 of European Economic and Monetary Union. Essentially, this means what? this means that European Central Bank is already created, but as we all know, euro was not yet circulating. It's still 1999. I will also be adding in here another timeline, which is the Greece and then European sovereign debt crisis. That was also in other countries, including Italy, Portugal as examples, and also Brexit and COVID-19, at least when the World Health Organization confirmed global pandemic. I don't want to make a causal statement using these. I'm just adding these there just for the sake of adding, just for the sake of mentioning in here some events of that are interesting from a financial perspective. Okay, this is the static analysis that you get from Poon, Rockinger, and Ton. Okay, so nothing changes over time. So dependence between extremes would not be changing over time. And what we're seeing in here is that starting from as time goes by, so this is in terms of UK versus France, as time goes by, there seems to be evidence of an increase between dependence between extreme losses in terms of these two stock markets between FTSE 100 and CAC 40. Okay, so then it peaks around subprime or so, it goes down a bit and it goes up again. So similar pattern can be seen in terms of UK versus Germany. So it goes up again, so it's reasonably in line with the value that was indicated, the static type of analysis that was indicated earlier by Poon, Rockinger, and Ton, but there seems to be some dynamic going on. And note that in terms of these charts, I'm focusing on these because essentially chi-bar is very, very close to one, thus suggesting that this would be the chart that I should be examining. Okay. So in terms of France, Germany, it goes up, it keeps going up. And the pattern is also similar as before. In terms of Asia, there's clearly not such a huge increase in terms of these extremal dependence in terms of at least over the period over analysis, and so this is up to then I think polite people to judge. My co-author mentions that perhaps there might be some effects related with trade as well as also related with other aspects related with also common currency that help also getting these things to happen, but that's definitely then to practitioners to go and have their insights. Okay, I'm presenting here a few more analyses, but I think in the interest of time, I just would like to also to conclude. I think take home is then similar across some of these charts. So we've introduced here Bayesian smoothing approach for time-changing extremes. Proposed approach defines a prior on this space of chi-t and chi-bar functions, and it's as easy to fit as a pair of generalized linear models. Clearly, you might claim, actually in practice, these changes might be more abrupt. So yes, definitely there would be room to include in your change points as well as, for example, using other basis functions and eventually even considering wavelets. And okay, there might be also situations where you have several covariates and whether you would like to do some regularization. Certainly that would be interesting. And that's it. Thank you.
Thank you, Miguel, for your nice talk. I don't know if you have any question.
I was just wondering about, so what you're actually estimating is like chi-u and chi-bar, they're finite to approximate the limit. And you're doing that separately for each one. So is there any way to jointly do that and enforce passenger dependence or
Yes. So this is something that I haven't included in terms of future work, but that I think it's natural because rephrasing the comment by Emma. So I'm essentially fitting two separate generalized linear models, but I could try to borrow strength across, and I think that's definitely something natural, and definitely even starting with thinking about what are the relations between these two measures would seem like the natural starting point. The marginals will still be these margins, but then definitely there seems to be opportunity for borrowing strength as well. And that would certainly be even more important when you have more competitors as well.
I guess it's tricky if you're doing like Caillou because they don't have the same constraints. That's the natural thing to do.
Yeah, exactly. So I guess the margins in terms of the likelihood, the YT and the ET processes that I was showing, I would keep exactly those margins. But then in terms of enforcing the constraints, I think I would need actually to go back to the relations between chi-bar to actually embed them also then in terms of the corresponding. But definitely the same logic. Yeah.
Any other question? Let me check online. But have something in the chat. When David asked about what's your opinion about the use of Fox processes in Python?
Yes, so in terms of use of box processes in Python as well, there's quite a bit of people working on it, including my colleague and friend Rodrigo Herrera. Also, Valdez Chaves de Moraes has done some related work. So, and I think that also touches on another interesting point that I haven't fully explored in terms of this talk, but that actually makes sense. So if I can go back here to a few slides, just to answer that question. So that's not working. Okay. Okay. So because actually in terms of their and in terms of what I'm showing in here is in terms of these probabilities of interest, but there's definitely room actually to have a look at what is actually the intensity function associated with the times of the joint losses. And this is actually something which I think is natural and it fits into the scope of this work, because when we work with point processes, then there would be room to describe whether there are periods over time over which you can have more concentration in terms of joint losses, and having a look at the intensity function and learning about the intensity function of the ZT would be very natural in this framework. So I think this would be natural to fit it into the scope. In terms of univariate approaches, there are some works that are developed, and point process representations of extremes also have natural connections with that as well. So I hope that partially answers at least the question.
I think so. Great, thank you, Aaron. Thank you for coming. Well, you can thanks Miguel again. Welcome to join us for the common group. Thank you everyone online. See you next week.
Thank you.
Bye bye.